The interviewer today is Vin de Silva. Vin is a professor at Pomona College in Claremont, California, and his research is in applied topology. So he was educated initially in Britain at Cambridge and Oxford, and then did a postdoc at Stanford from 2000 to 2005. It was there that he started working with Gunnar on a number of projects in applied topology. For example, analyzing natural images, zigzag persistence, etc. Other sort of very famous contributions include work with Robert Greist on the use of homological methods in sensor network, and work with Josh Tenenbaum on the isomap. So with that, I will let Vin take over and ask Gunnar about sort of his story.
Thank you very much, Sarah, and thank you everyone for being here. Hey, it's truly an honor and a pleasure to interview you, Gunnar. It's been a while since we got to see each other, and on a personal level, like as Sarah said, my research career has been in applied algebraic topology, which is a field that wouldn't exist without the work that you were central in doing, and certainly some other people too. Now, for everyone here, Gunnar is an emeritus professor at the Department of Mathematics at Stanford University. He held the Anne and Bill Swindells professorship and was chair of the department back in 95 to 98. In 2017, Gunnar was elected as a fellow of the American Mathematical Society. Gunnar is known for work in actually a number of different fields. So homotopy theory, algebraic K-theory, back in 1984, the proof of the Graham-Segal conjecture. And as many of you here will certainly know, Gunnar has been one of the central figures in applied algebraic topology. He's also the co-founder and was the president of the predictive topology company, IASTI. So with that, yes, let's get started. First of all, how are you doing? It's been quite a while, as I say.
I'm doing very well. I hope you are too. Even in these challenging times. But yeah.
Yes, it's.
You're teaching remotely, I imagine.
Teaching remotely, trying to, stay out of the pandemic as best we can while things roll back in. Yeah. It's a little bit. I'm doing well. It's a little bit cold in Pasadena. This isn't. Okay. This isn't why I moved from England to California, but I can't complain. So the first few things I wanted to ask you about, Gunnar, are maybe to do with geography, right? So you were born in Sweden, but then you moved to the United States at a certain age. Mm-hmm. What was that transition like? And I'm also curious about your experience of mathematics before and after, and the education system.
Yeah. So actually, we moved in two steps. So we first came over to the United States when I was 5, but returned back to Sweden, and then only came back to the US for good when I was 10. And it was actually extremely valuable, I think, to have those moves back and forth. I think it gives you, a way of thinking about people, because you start to see how different people are and cultures are different and so on. And so seeing that at an early age allows you to appreciate that rather than to be frightened by it. Now, mathematically, what I would say is at that point, now, of course, I don't know what the Swedish system is like now. I'm not a part of it. But I think what one could say is that the US system, I found, was sort of more encouraging of people trying different things and doing new things and so forth. So mathematically, it's hard to put much of a distinction on it, though, because again, these are early days. I haven't had experience with the PhD part, or even the undergraduate part back in Sweden.
Yes, I had a similar experience just in terms of moving from Sri Lanka to London and back again, and then back again.
Yes.
What you say is really like you just get used to, the way that some of our basic paradigms are contingent on where we happen to be.
Exactly. Yeah.
And my move to the United States kind of exactly what you said when I came to Stanford as a graduate student is just seeing even within mathematics, there's an enormous flexibility in PhD programs. You have time to figure out what you want to do. So then I'm wondering then, was it always, when did you start to know that you really wanted to pursue mathematics?
Yeah, so that's a great question. I thought about that since we're thinking about this interview. And for me, I don't know, most people here are young enough that maybe you're not familiar with the term Sputnik, but Sputnik was the first satellite launched by the Russians, and I believe it was December of 57. Or perhaps a little earlier in 57. Anyway, 1957. And my dad, it was a radiologist and a sort of research radiologist, actually cardiac radiology. And so he was very scientifically interested in everything, but not mathematically so. But he saw this, and he said to me, as a little 5-year-old kid, he said, "Look what they're doing with this. You know, they can send satellites into the into space. They can predict when an eclipse is going to come. You know, they can do astronomy and so on. And the thing that's in it is all mathematics." He said, "So you should do mathematics. That's the thing. That's the way of the future." And I think a lesson that I learned from that is, now he then went on, I should say, when we then celebrated my 50th birthday party, and we were talking about everything, and he said, "We'd encouraged all this math stuff with you when you were young, but we didn't mean for it to go this far." But I think what it does say is, it's the way that you think about yourself and so on is can be so affected by someone giving you a definite path, or someone showing you, boy, they would really appreciate this. So for me, as a 5-year-old, to say, "You should do this," my God, I say, "Yes, I'll do this. I want to do this." And so that is how it happened. Now, it was then encouraged tremendously by sort of teachers along the way. I had some very great teachers in high school who led me to focus more on it and so on. But I would say that was the starting point.
It's actually really refreshing to hear, what you're saying that your father said when you were a young age.
Yeah.
Like I certainly know that in a lot of my time doing mathematics, I've lost sight of the fact that it's so incredibly powerful, like that it really,
Well, Vin, that actually, and I continue to learn that now. I think, and maybe you're saying the same thing. That I think sometimes we get caught up in the beauty of the subject, and so that so we and I think there's a lot of value to that. But what we lose sight of the fact also that it can solve problems. I think that's what we're trying to do with TDA, is trying to make sure that we sort of continue to understand that it's solving big problems. It's not just a beautiful edifice, but it's a tool that should be adapted to the circumstances and to solve all sorts of problems. And I think the origins of it are really in physics, where the models are very, very precise and and very justifiable, and one can prove things about them. And I think we're moving into this continue to move into this more stochastic world, where things are, at least for the moment, not as idealized and pretty. I think they may get to be that way as we get further into it and but we should not be afraid to sort of get our hands dirty, even if it's not the prettiest of models, if you know what I mean.
Yeah, I absolutely know what you mean. Like I remember before I moved into to work with you and also Josh Tenenbaum in these applied kind of realms. I was a low-dimensional topologist in my PhD, and I realized that the beautiful streamlined theory, the work of Milner and Smale and those kinds of things, so polished, right?
Yeah.
And it was a shock to enter the real research field and realize how messy everything was, because while people are trying to figure things out, it is that way.
So, no, and here's another, I would kind of add to this though. So the next step here is to say, well, actually we've built a lot of tremendously pretty stuff and useful stuff, and maybe we're not taking full advantage of it yet. So I kind of view, applied topology, we're now in a position where, we're doing mostly direct computations of persistent homology, and then there are other aspects of it, obviously. But what I would say is, there's all this machinery underlying homotopy theory, which is cup products and cohomology operations and so forth, as well as kind of Meyer-Vittoris sequences that kind of tell you how to go from local to global. And I think all those things actually can be leveraged in computational topology. We just aren't quite there yet. In this evasion problem, as you may know, there's a kind of a cup product approach to it, which I think is quite promising. But I think overall, we should now be looking at, let's take some of the infrastructure that's been built, let's take the easiest stuff first, but let's gradually incorporate it into what we do.
So then, one question I want to ask you about that is that, so in order for a research field or for the people in the field to do certain things, there's going to be a sense of urgency, perhaps, should come from somewhere, right? And so so my tendency has always been to retreat into how pretty the mathematics is and how
right.
But then I've noticed in working with you that you really prioritize trying to find actual motivating problems. Mm-hmm. I'm just curious to know, because also the work that you did before was in pure mathematics, and I'm just wondering how the type of motivation may have changed in.
Well, yeah, the type of, but what I would say is, even in pure mathematics, I think one still wants to do things motivated by problems. So, and actually I will sort of mention that my thesis advisor, Jim Milgram, kind of imprinted this idea very strongly on my psyche, so to speak. I think he started talking about, vague notions of machines, and he would say, yeah, but what problem can it solve? And mathematics is full of big problems. I mean, if you mentioned Milner's 7-sphere, I mean, that is a fundamental thing, to find that you can actually get at the smooth structures on a sphere. And there have been numerous examples of that within the field of algebraic topology. Various conjectures that, the Poincare conjecture is perhaps the most famous, but many others that solve actual problems. Now they don't have to be problems that have, applications outside of mathematics. It's quite okay to solve intellectually interesting problems in mathematics. But I guess my preference is always to build something towards solving a problem where there's a chance of failing, and as opposed to simply building a pretty machine, So I just, because, and I feel like the machinery and the theory gets better if it's driven by the need to solve a problem. You find things that are surprising in a way that you wouldn't find if you just develop machinery.
So it's almost as if you have this target, it forces you to cross certain terrain that you might sort of sail around.
Yeah. Look, for example, there's the whole world of motivic homotopy theory, that's applying topology to number theory and algebraic geometry instead of to data. But it's a similar stretch. And there's some work that's done around saying, well, what things in ordinary topology, how do they play out in motivic theory? But one could also take it from the other point of view and say, well, look, what are some problems in algebraic geometry? How do I have to modify the theory? What are things that don't occur in the ordinary theory that I have to add to the motivic homotopy theory? And I think those are huge contributions. And the idea of working on such problems in algebraic geometry and trying to see how can I adapt homotopy theory to solve them is more challenging, but in the end more productive than simply pushing the analogies.
So then I wanted to pick up on a phrase that you used a moment ago. So to you, is there a strong connection between doing something, you know, that's useful, effective, powerful, and trying to do things that have a chance of failure? Like, I really like that phrase.
Yeah. Well, you see, I feel like if there's no chance of failure, then you see, yes, there's a way that I could carry this out. And I think, you know, what that says is somehow the innovation has already been done in your mind, and maybe it's very useful to put it out there. But you get forced to challenge yourself if you've got a problem, and you get forced to challenge the technology. And so, you know, you might say, this is not something I would have even thought about that topology could do. You know, and this is ways of using topology that I think, you know, might be very different. Let me say, even to the point of view of saying, well, what should the emphasis be? So one of the things that happened to me when I first started going out and talking about the persistent homology, and I would talk to colleagues in the math departments, and you know, many of them have not worked on any kind of applied stuff, and they would say, gee, you know, you only seem to use homology in dimensions 0, 1, and 2, and maybe 3, but what about 57-dimensional homology? You know, I like all those higher dimensional homology groups. And of course, the answer from our point of view is that, you know, you can't, you know, 57-dimensional homology, unless you do something interesting, is not something that ever comes up in data, just because you can't even build a Vittoris Rips. I mean, it's hopeless to do that. And so from my point of view, I've kind of been pushing the idea recently that topology, you know, is at its maybe a very fruitful direction that is going to solve more problems than going very high dimensional, is instead to go low dimensional, but to go with a reference map to a base. So, you know, in topology, there's this notion of studying not just spaces, but spaces with a reference map to some base space B. And the set of invariants of those things is much richer. So for example, the cohomology, instead of just being a ring, is an algebra over the cohomology of B. So it's very much richer. And so my feeling is that, you know, that even within topology, in the ordinary topology, when we're looking to apply it to mathematical problems everywhere, my sense is that it's richer to do low dimensional invariants of this kind of, you know, relative kind of topology over a base than to aim for the very, very high dimensions. And of course, this is just a generic statement of lots of things which could be, lots of problems that could be addressed in mathematics or in topology by the higher homology groups. But I just feel like that area, the area of, you know, relative topology in low dimensions, is so full of rich invariants that it ought to be exploited.
And then, if I'm understanding correctly, this is really inspired by, I mean, Grothendieck made a real push for taking the relative perspective in everything, right?
Well, you know, yeah, there's a whole approach to, you know, Fermat's theorem. Now, you know, it was that you know, has yet to be completely worked out, but that involves exactly what I'm talking about. That is to say, you know, the Fermat curve is actually, it can be viewed as a space, but sitting with a map to the so-called classifying space of the absolute Galois group of Q. I realize I'm getting into the weeds here, but you know, there is this space, and it's actually a K-pi1 space, a space whose only homotopy group is in dimension 1, and the maps to that encode a lot of the arithmetic information that is believed, and that was exactly this Grothendieck's 1,000-page manuscript or whatever that discussed this. Yes.
So then on a slightly speculative question is that I'm just trying to place this idea of, you know, there's a space and a map to another space. Another way to think about it is that there's data equipped with a map to some measuring space. And so this sounds a lot like the kinds of things that go on in machine learning. And I'm just wondering if that...
Well, I think so, but absolutely, you know, so, you know, one could view PCA1 as your first map to the real line, and maybe one now studies what happens over that. You know what the next term is, and so I would actually point to some work I've done, or I should say my student Brad Nelson has done, which is talking about data analysis over a base, And let me say, and I think you'll appreciate this because it goes back to our work on the Klein bottle and so on. So one of the things that happened in there that when we studied, and Vin was the driving force behind this, I got to say, the densest part of the so-called Mumford set of 3x3 natural images. And, initially we found what we call the primary circle, and then with a different density estimator, I remember Vin coming into my office and showing me, oh my goodness, it's 5, there's rank 5 in the homology, which was consistent with a certain graphical model there. So that was all very interesting and exploratory as a form of exploratory data analysis. And then we made a leap. We said, well, where does this 3-circle model fit? And we saw that it fit inside a Klein bottle. But it was very difficult for us to find the notion of the actual Klein bottle in that data set because of the fact that there's varying density depending on the angle of the lines and edges. But so here's a way that one might do machine learning, as I think you're proposing, Vin. So suppose we take our very first insight, which was that you have this primary circle, which, by the way, consisted of fundamentally linear gradients just at different angles. And so it's talking about directionality of a patch. That could give us some insight and say, look, there's directionality here. So now let me build a directional, a way of teasing out the direction. And this is what, Brad showed, that you can do a particular form of this, which works very well. And you can say, I'm now going to consider my data set as a data set over the circle. It comes equipped with a reference map to the circle. And so now I can say, and as he does in his thesis, let me now compute density, average density at every angle. And so what I will find is that on that circle, there's a great deal of variation in the density. And so I can normalize for that. I can say, look, actually, I'm only going to take, I'm going to take my percentage thresholding for density. I'm going to allow it to be variable with angle. And I'm going to have it be some percentage of the percentage in that angle. And when you do that, then the Klein bottle comes out very naturally. So I sort of echo, I would agree very strongly with what you say, Vin. That is to say that if one can view data analysis as this iterative process where you take some insights and you use that to then inform what you do to the next layer, then that's a hugely powerful thing.
That's a very beautiful way to do this. Like, as someone who's worked with you on this Klein bottle for pretty close to 20 years now, maybe about 18 years now, it's there's something really nice about hearing that there's a way to get it to really emerge versus being a faint trace in the data. That's really superb news. So I have very vivid memories, Gunnar, of the first time we saw those 5 lines in the persistent barcode. That was I think I had the mistaken idea that the as you rotated that it would fit into a sort of torus.
I know.
And I remember a day or two later coming into your office and there was a certain excitement about the fact that, the Klein bottle, which is the stereotypical, classic topological space, just sort of showing up there. I just wonder how you've
this to me this is something that one learns about humans also. In other words, I think it's extremely fortunate that it was the Klein bottle and not the torus. And the reason, I mean, of course, scientifically, both would be equally useful. But I think it's something where, people get excited about sort of new and sort of slightly interesting and quirky things. And so, maybe it even sounds a little cynical, but my feeling is that it was very fortunate that it turned out to be a Klein bottle.
Yes, going on the cynical theme, but obviously there's a genuine thing here, is that the Klein bottle is certainly more marketable, isn't it? It's more it's memorable, right?
Exactly.
And in fact, I remember a wonderful thing that you did at one of these early conferences in the field. I think you had gotten in touch with the Klein bottle maker, I think, who lives in Oakland, and I still have my Klein bottle. I think a number of people have this glass Klein bottle.
Well, I have one that you gave me, in fact. So yes, I have multiple Klein bottles sitting around the house, but I think my favorite one is the one that you gave me. So there you go.
I want to talk a little bit, something that we've been touching on. So there's a phenomenal essay by William Thurston. I don't remember the name of the essay, but I can look it up for later, where he talks candidly about, first of all, his 1970s work in foliations, and then the work he did after that, obviously with the geometrization conjecture, and there's the huge, three-manifold program. And what he said, I've actually been somewhat haunted by since I read it, which is, he said that his early work in foliations, he just thoroughly did everything he could, and he had lots of results that he pushed through and finished, completed them, and then the result he found was that it killed the field because no one wanted to work in it. Like he had, and so he very consciously, when he moved to his work on three manifolds, he very consciously he didn't follow through on everything. Like he wanted it to be something that would be attractive ground for people to move into. Like if you're a graduate student and you want to move into something that's, do you want to move into something where the experts have already done it, or done 99% of the work, or do you want to move something that looks like it's full of, and I was very surprised to hear that that was a deliberate policy, and I think it was genius. I mean, and so from that, what I really want to ask you is, I had a ringside seat to watching you have a huge part in creating a field of research. And so it's not just the theorems and the applications, it's also going out, it's getting funding, it's deploying funding, it's talking to scientists. And I would just love to hear your side of how you did that, and what parts of it were conscious and what parts in hindsight that maybe you can see that went well.
So the first thing is, I would never say that I would be in a position that Thurston was in to sort of kill a field by doing all the work. That's that option wasn't on the table. But what I would say is, yeah, it did require some readjustment. I had to think about, and I had to do some serious thinking about, why am I doing what I'm doing? Do you know what I mean? In other words, there is a natural way to proceed, which could have been and just continue to prove theorems. And that would lead a certain way, and there would be some number of people that would be interested. But there is always this danger, because of the way that mathematics is organized around conjectures and so on. When you kill a conjecture, you prove a conjecture, you may actually kill a field. And so I think one of the things that I want to be conscious of is that there are actually different aspects of evaluating mathematical work. So within mathematics, we often think of, well, how deep is the theorem? Okay, that's good. We sometimes think also of how hard is the theorem? How hard was it to prove it? And in a way, I think, yeah, maybe that's a reasonable way of evaluating things. But what one really should be doing also, seems in my mind, is to say, am I doing something which will help others do additional work? Can we not only not kill a field, but can we open it up so that there's so many more people who can add their ideas? And I think inherently that field, topological data analysis and in general applied fields have more of this happening in it than pure mathematics does. And so that's first a general thing. I feel like we should make sure that in mathematics we value things that enable other people to do things as well. That should be a strong value point. But yeah, then in terms of certainly putting together big grant proposals to NSF and DARPA, and then later things for the company and so on, those are all things that followed from the desire to make the subject big, to make the subject something that everybody can use and everybody can do things with. So it wasn't, once that decision was made, then it wasn't so hard to figure out, well, you know, how do I do these things? Because they're not fundamentally hard, the grant stuff. Although what I would say is that it requires the ability to learn to communicate things very effectively. So hopefully I've done some of that. I know that that was not a strong suit of mine before going in this this route, you know, as many will probably tell you. So I think it's been a huge learning experience for me about communicating things, which, you know, I wouldn't have given up for the world. So
yeah, my memory of it was just being very impressed at your commitment to going out and talking to scientists, you know, also talking to people at the funding agencies, but really going out and spreading the word to the scientists who might not know that this is something that could be of value to them. And that takes going out and doing it. You know, one thing I wanted to follow up on, Gunnar, is that what you just said about the value of the work being, you know, we should also measure what it allows other people to do.
Yeah,
I really appreciate you saying that, because I've come to realize that that's one of my, maybe that is my primary motivation when I do research.
yes.
I really want to write papers that are so transparent, no matter what the initial apparent difficulty is, that are so transparent that anyone who reads it is immediately able to go out and prove their own theorems or do their own applications.
Exactly. Yeah.
And I wonder if the culture, that culture sort of does need to be actively encouraged, because there's the default is that if it looks difficult, then it's easier for people to assume that it's more valuable work.
Yeah. Now I will say, I don't think that's a fundamental problem with everybody. It's somehow the way that we've set things up. It comes historically, you know. I think, you know, Pythagoras, Fermat, and so on. We've set ourselves these tasks because they're hard, and we know that it will challenge us. But this other point of view, my sense is that in talking to students, as I talk to younger people, I think they're quite open and happy about that. In other words, I don't think it's a huge battle that has to be fought to get this across to everybody. I think many people are seeing it, are seeing that now, and are working in those directions. Mm-hmm. I mean, do you agree? Don't you see that with the young people?
I certainly see, yes. Like, I feel like maybe something changed from my perspective maybe 25 years ago, which is, for example, collaborative work, which is in many ways such a powerful way,
yes,
for human beings to sort of progress.
That's right.
Is much more understood as being like, you don't have to be hoarding up the single author papers to be regarded as being an important part of the field.
Exactly. Yes.
So I wanted to ask you now a little bit about, so I experienced you as an absolutely fantastic postdoc mentor. Like at the time, I really valued the way that you gave me space, but also gave me, you know, really strong directions to work in. And then looking back, I've just only come to appreciate it more. Yeah. And I'm really curious about your philosophy of mentoring, you know, your PhD students, your undergraduate students, your postdocs, and maybe also relate it to how you worked with Jim Milgram, your own PhD advisor.
Okay, yeah, let me take those. So on mentoring graduate students and postdocs, and frankly, even undergraduates, you know, Henry was an undergraduate with me as well. I mean, you have to keep in mind the goal first. The goal is to help someone become an independent researcher. Okay. Now, it's the difficult step to go, because when you don't, if you've just done coursework in mathematics, you know, the idea of actually going out and doing a problem that hasn't been solved before seems very, very daunting. And so you need a lot of guidance along the way. And so my philosophy with graduate students, and to a lesser extent postdocs, is that let's do something relatively easy that we can see the answer to, what it might be, and I'll guide you a lot on that. But then I will want to ask you to say, well, okay, so what do you think is the next problem? And and particularly with postdocs, I really want to know what problems are moving them, and then let's sort of see, well, okay, so what are the techniques that we need to do to get to that point? And if those are ones I can help with, then let's do it. Otherwise, maybe I'll point you and say, maybe Leo Gibas can help you with this. If you, the computer scientist at Stanford, maybe someone else can help you with that. Now, so that's kind of the general philosophy. Again, keeping the final goal in mind, which is to get someone who can make full use of their abilities in thinking independently about problems. That's the end goal, and so everything is directed toward that. Now, what I will say is that Jim was someone who, Jim Milgram, was someone who sort of made a fundamental shift for me, because I had just been doing undergraduate math courses, and I sort of thought in those undergraduate math terms, and even graduate math in terms of kind of formalisms and so on. And I think the fundamental thing that he said was, always compute. Make sure you always compute, because you always learn something. Don't just think about theory, but make sure that you compute examples. Do as many examples as you can. And he said, and also keep your mind on the problem. So yeah, I would definitely credit him with a lot of influence in that direction.
Would you say, like, what that makes me think of is, what are the things that we do that can kind of keep us in contact with the hard edge of reality? And so, for example, when I'm teaching an undergraduate, maybe an advanced undergraduate, they might think that they have a proof, but the hard edge of reality is trying to writing it down and seeing how it. And it sounds as though, like, if you have a theory, but you need to be able to compute with it to know that you have something effective and see where it becomes jagged.
Yeah. So let me tell you about an experience I had. So I taught, and actually Sarah was a TA for this course, taught applied topology to undergraduates at Stanford. I did a course 1 year like that. And it was full of students, about, I think, half math and half CS, or half computer science. But I took the point of view, so the way we ordinarily teach topology is we say on day one, we define a topological space, and then we give examples. And frankly, I think the answer is that what happens is sometimes we lose about half the audience right there. And so in doing this, the course was in applied topology, but we taught about simplicial complexes right away, and homology of simplicial complexes. So there were things that they could compute on day one or day two. In other words, just using linear algebra packages and so forth. And so I think that was tremendously useful, because they all got in. I don't think we had much attrition at all. And the computer scientists were as engaged as the math students. Now, over time, then we start to sneak in, the medicine and so on that comes later, so we do simplicial complexes and we can work with that. But then when we then say, this thing with simplicial complexes is great, but sometimes the spaces we see don't come triangulated. They don't come with as simplicial complexes. They just come as spaces. And then you can say, well, then there is this thing called singular homology, which is defined for all spaces and is functorial and it's very powerful. And they can understand the need for it at that point, because they've already worked with problems where they had to triangulate things, and they can see how onerous that is. And it also points to the need for some of the more high-tech things we do. So I kind of separate, I would call direct methods versus indirect methods. So direct methods are where, you build a Vietoris-Rips complex and you just compute its homology. You let the computer compute its homology. But indirect methods are more, Meyer-Vietoris methods where, you compute pieces and go local to global, or whatever it is, all the high-tech stuff that we do. And I think it's much easier and much better to motivate the high-tech stuff if you've been through these definitions at first. So I started advocating, this is one of the last courses I taught actually, but started advocating for that we ought to teach ordinary topology to undergraduates in somewhat the same way. In other words, that it ought to go from, they ought to be allowed to do something right away, because being able to do something is something much more motivating than sitting and taking received wisdom from above and, you know, proving little exercises about it.
I'm really glad to hear you say that, Gunnar. You know, so when I was about 9 or 10 years old, surprisingly in my, you know, inner city London primary school, I remember very vividly the teacher coming in one day and telling us to draw pictures and count nodes and edges and regions. And I even have a feeling that we had to do an alternating sum, and we were like, you know, we were just drawing pictures.
Yes.
But so then, okay, so then there was essentially no geometry in my mathematics education except for this very stringent Euclidean geometry in secondary school. I get to college, at university, it's not until the final year that we have an algebraic topology class.
Yeah.
And my memory of it was that many of my classmates, you know, very proficient, capable people, regarded it as this weird, esoteric subject, because the way it was presented, you have to have, you know, all this analysis, all this point set topology, all this algebra and, you know, modules and all of this. And then and only then were you allowed to sort of try to do things with this.
Yeah.
So then when I came to work with you, this had been a burning question for me. It's like, come on, like this is some of the most fun and also powerful and direct instances of mathematics, and it's hidden from so many people.
Yeah.
So starting to work with you and sort of hearing about this philosophy is, yeah, you just go straight in, give people the simplicial complexes. Don't worry about the modules. Go straight in with the vector spaces, because they've all done linear algebra.
That's right.
So I had another bunch of questions. Yes, actually, so I wanted to maybe switch a little bit in the last few minutes. You've talked a little bit about this, but I know that you've made various big shifts in your intellectual and professional career. Now, this is not that you've let go of the previous stages, but it's more that, and so the three that I'm thinking of are your early career with the homotopic theory that you still maintain, and then the shift into this applied world, and then finally the shift also to be in the business world with IASTI.
Yeah.
And I'm super curious about how you experience those changes.
Yeah, let me say, so it's kind of, I think, first of all, this shift to business, I think one learning is, you know, people tend to think, well, okay, so, you know, you do the intellectual work in academia and then the business work is grunt work and so on. But in fact, the business world is also a huge intellectual challenge. In fact, it has something in common with the challenges of teaching, I would say. So when you're going out and trying to explain to people why your product is useful and so on, you have to explain it to someone who is not captive. You know, the undergraduate students are somehow captive, and they kind of have to listen because they need to get their grade and so forth, you know, and in many cases they're motivated as well, but, you know, not always. But these people may be actively challenging you because they don't want to spend their money necessarily. And so, you know, so you have to talk about things in a way that's even broader. So it goes even beyond the idea of giving a public lecture in mathematics, but it's got to be, you know, you need this for this and thus and such a reason. And also it's kind of an extreme form of doing mathematics to solve a problem, right? You're doing mathematics to actually, you know, please or, you know, satisfy a customer. So, but the surprise for me was how intellectually challenging that was. And so I actually really enjoyed that. Now, what I would say is going back, yes, the applied topology stuff, you know, in academia continues. I'm really excited about the work that we're doing there. But even the old stuff, I'm actually, there's a project that I'm embarrassed to admit is now, you know, 31 years in the making, which I'm just completing with a collaborator. And, you know, over time, we've had to write a lot of papers around it. But anyway, it's taken perhaps potentially longer than it should. But on the other hand, it's a very hard problem. So I kind of like to keep all these directions going at the same time. I find it is not conflicting, but actually it is instead kind of a synergy. They feed into each other, frankly, because you keeps your mind nimble, in my view.
There's something very heartening about hearing about this 31-year-old project.
Yes.
Because what it says to me is that we live in a society and in a structure where there is room for people to work on important things over a really long period of time, and then now the fruition of that work is going to...
Right.
Yeah. So I think we're coming to the open questions part of this.
Okay.
I just have one last question, which is what advice do you have to a young mathematician these days?
Yeah. Well, I would say what Jim Milgram said to me: make sure you compute examples. That's at a very low level. But also just, the way that we've motivated people sometimes is to say, Poincare conjectured this, work on the Poincare conjecture. Well, what I want to say to people is actually, that's all fine and good, but you are also responsible for making up the problems that you work on. So you should think very hard about what it is you want to do and want to accomplish and so on. I mean, I realize that there are career issues and so on, but keep in mind that the North Star should be not necessarily that you're solving problem to say that you solved an old problem or you solved the problem that, so-and-so suggested, but rather that you create a problem so that people can say, oh my God, this was so clever to even think of the problem, to pose the problem. And so I would hope that all of us think about those problems, and we all generate problems for each other to solve, rather than setting a few high bar ones, which everybody then works on.
Thank you so much, Gunnar. It's really been a pleasure.
Yeah, same here, Vin.
Thank you so much, Vin and Gunnar, for the fantastic interview. So I have a couple of questions for you. So first, Gunnar, how did you first even hear about persistent homology? I mean, how did you find this paper by Adelsbrunner and Letschiff and Zomerodian, or what was your route to even be exposed?
No, the route was actually, I only discovered the paper kind of after writing the grant proposals, and I found out that there had been some work done already. In other words, I've been thinking in those directions, but not put it together in the way that they did. So that was kind of the idea. The idea that you should have a directed system of Vittorius-Rips complexes. It's a great idea, which I think Vanessa Robbins, was the initial one on. And so it's a beautiful and natural idea.
Oh, that's fantastic. Vin, a question for you. You sort of had a switch in fields as well, I would say. How did you become a postdoc working with Gunnar?
Oh, so I mean, the honest answer is that I found that my original field was too difficult for me, in the sense of the balance between what I thought I could do and what I was motivated to do. I both enjoyed it and struggled with it. And so then there was this opportunity to work both with Gunnar and with Josh Tenenbaum on something that very suddenly seemed like a door had opened. Like there's all of this beautiful mathematics in topology and in manifold theory. And suddenly I was introduced to this possibility that you could use it on data. And so I rushed straight in. Like I enjoyed the chance to be maybe at the, let's say, the low-hanging fruit part of a field versus the very opposite situation where everything was very intense and very complex.
Fantastic. Gunnar, so I wanted to ask you a tough question. So you mentioned the importance of taking on tasks where there's a chance of failing. So I was wondering if you could share with us a couple, or maybe one in particular, moments where you felt like you failed, even if only temporarily, or initially failed.
Oh, well, absolutely. Actually, they're sort of too numerous to describe, but I'll just tell you one. There was a question that I was very interested in about transformation groups acting freely on products of spheres or on finite complexes. And I had a very strong belief that certain things should be true about those, that, you know, and that it should be relatively straightforward to prove from algebraic methods. The idea was that the sum of the Betti numbers should be greater than 2 to the k if the group Z mod 2 to the k is acting on the space freely. And, you know, well, now it's been proved that, in fact, there aren't space level examples, but there are chain complex examples that go against exactly what I said. So, and frankly, that I started working on that in the mid 80s, and, you know, sort of thought it was true for 20 years. And it was something that I was sort of always on my burner and thinking it was true. So, you know, that's a failure. I think the answer, though, is, and my wife pointed me to this just yesterday, that there was somebody who said that, you know, failures are a part of success. You know, if there were no failures, then there would be, well, it's hard to think of what success would mean. And furthermore, you kind of explore, you learn so much. You learn from the failures things that allow you to succeed at other things. So.
Thanks for the advice. So another question that was asked was, you mentioned this incident when your dad mentioned Sputnik to you and the value of mathematicians. How did you sort of decide you wanted to become a math major? Was this something you knew in high school, or was this something that you came across in college?
Well, so in high school, I mean, I was a math nerd in high school. You know, I was in the math club and, you know, all this kind of stuff. So I think I already wanted to do mathematics. I think I didn't have a clear picture of what the career path would be until I got to college and found, oh my God, you know, I can get paid for teaching this and for doing research in this area. And so then I thought I would set myself, I definitely wanted to be involved in that. And so, you know, at that point, the focus became clearer. But what I would say is, it was clear to me around age 12 or 13 or 14 that I wanted to do something around that.
Mm-hmm. So I think I have 3 more questions. So one from Tamal Day. What is your view on the role of the synergistic connections between algorithms and mathematics, and in particular in applied topology?
Yeah, I think they really are very synergistic. And let me actually give an example, because so, and this is, I'm pointing out to a paper that we have relatively newly out with Brad Nelson and Anja Dwarka. See, so let's think about the high-tech version of algebraic topology, which is where people do it by hand, you know, and that's calculating from local to global and so forth. And so that's really important in situations where you can't do it with computers because the space isn't given to you in the right form. But it turns out that if you think about that methodology, its role in computational topology is to shrink the computations. So, you know, what was impossible is now just really onerous, and, you know, but can be done more effectively with these methods. So I think there's this huge interplay, and of course the other way is so important also. Whenever you try to compute something, you immediately learn things that suggest, you know, various theoretical constructs. You know, those considerations are really quite fundamental in my view. Yeah.
So Jose Pereira asks an interesting question. He asks, what's your impression of how the mathematical community perceives the field applied topology, and how that has evolved over time?
Well, I think it's evolved, you know, really nicely, actually, you know, faster than I would have thought, and better than I would have thought. I mean, I would point to the fact that, you know, in you know, the math reviews or the classification system that AMS uses, you know, we are in that system. And I think there's lots of papers going out now, and, you know, special issues of journals, you know, journals have been formed, a lot of meetings. I just think that the energy is fantastic around the subject. And we're just finding more and more ways to apply it. Even people outside of the subject, people outside of mathematics are seeing it. So, and I think it's being received well within mathematics. I just see much more of it appearing every single year.
Mm-hmm. And then one final question before we return to Sarah to wrap this up. What do you think of the prospects in applied topology related to machine learning?
Oh yeah, Absolutely. So that's what I'm involved in right now. That to me, that's a really exciting area. So, specifically within the idea, within the context of deep neural nets, I think there's a tremendous amount to be done there, where you can use these methods to lessen the amount of data needed to learn for a particular problem, and also to get better generalization and get better transparency into algorithms. So I'm really excited about that work. Yeah.
Okay, thank you. I think that means that we're done with questions. So I want to thank Vin and Gunnar again for this wonderful interview.